Hi, we're here to introduce LaserMix, a framework for semi-supervised LiDAR semantic segmentation. LaserMix is a data-efficient learning framework designed for LiDAR segmentation. It leverages the spatial prior in driving scenes for data-efficient learning. It constructs low variational areas via laser beam mixing. It encourages the model to make confident and consistent predictions before and after mixing. It achieves competitive results over full supervision counterparts with 2 times to 5 times fewer annotations. Our framework can achieve promising results under a limited annotation budget and is robust across different kinds of point clouds collected by different LiDAR sensors. The 3D perception using LiDAR point clouds establishes multiple tasks for achieving safe operations of autonomous vehicles. The LiDAR sensors provide accurate depth sensing abilities, robustness against the low light conditions, and dense perceptions, which have been widely used in autonomous driving systems. LiDAR semantic segmentation is one of these important tasks for 3D scene understanding, which aims to assign a semantic label for each point in a LiDAR point cloud. The annotation of LiDAR point clouds, however, is very expensive. Taking the popular Semantic Kitty dataset as an example, annotate a single frame in this dataset costs up to 4.5 hours, which is much more expensive than annotating an RGB image. Recent work resorts to weak annotations to ease the budget. For example, in the Scribble Kitty dataset, the LiDAR scans are annotated using line scribbles, which reduce the time cost to 10 to 25 minutes each. However, the huge amount of LiDAR data still constrains the annotation process. In this work, different from previous pursuits, we target on the less explored semi-supervised LiDAR semantic segmentation. Our goal is to leverage the abundant raw LiDAR scans for training accurate segmentation models. We propose LaserMix to make the advantages of the spatial prior in LiDAR scenes for effective learning with semi-supervisions. Unlike the general 2D or 3D segmentation tasks, the spatial cues are especially significant in LiDAR data, while certain glass tends to appear at certain areas around the ego vehicle. LiDAR point clouds serve as a perfect reflection of real-world distributions, which is highly dependent on the spatial areas in LiDAR-centered 3D coordinates. For example, the top laser beams travel outwards long distance and perceive mostly vegetation, while the middle and bottom beams tend to detect car and road from the median and close distance. We propose LaserMix to mix laser beams from different LiDAR scans, and then encourage the segmentation model to make constant and confident predictions before and after mixing, which can be general across different LiDAR representations. As a result, our overall pipeline significantly outperforms previous state-of-the-art methods in both low data and high data regimes. The LaserMix operation follows a 3-step procedure, partitioning the captured LiDAR scan into low variational areas, efficiently mixing every area in the LiDAR scan with foreign data, encouraging the LiDAR segmentation models to make confident and consistent predictions on the same area in different mixing. Here, the mixing happens along the inclination and azimuth directions, which can be calculated by the point coordinates as shown in these equations. This figure shows an illustrative example of partitioning points into different areas. The laser partition effectively exerts a strong spatial prior in LiDAR point cloud. Since the cost for directly computing the marginal probability on real-world LiDAR data is prohibitive, mixing LiDAR scans in this way helps to efficiently reduce the training overhead. This figure shows our overall pipeline. There are 2 branches, one student net and one teacher net. During training, a batch is composed of half labeled data and half unlabeled data, We collect the predictions from both networks and produce pseudo-labels from teacher net predictions with a confidence threshold. The unlabeled scans and the generated pseudo-labels are mixed with labeled data via LaserMix to produce mixed data samples, which are then fed into the student net to compute the mixing loss. We provide detailed derivation and examples in our paper to theoretically prove the effectiveness of our framework. We established a diverse and comprehensive semi-supervised learning benchmark on Semantic Kitty, NewScenes, and Scribble Kitty. To compare between different modalities, we implement our LaserMix framework on two LiDAR representations, the range view and the cylinder voxel. We randomly sample 1, 10, 20, and 50% labeled scan and assume the remaining ones are unlabeled. The results show that LaserMix can significantly improve the model performance under semi-supervisions. Such an effectiveness holds across different datasets and different LiDAR representations, and is especially evident in range view, which reaches up to 11.2% MLU improvement. We also transplant a similar idea on the image domain and achieved better results than the state-of-the-art semi-supervised image segmentation models. The component analysis in this ablation study shows that LaserMix contributes significantly to the overall improvement. Meanwhile, using the teacher net instead of the student net to generate the pseudo-labels leads to better results, as the former is temporarily ensembled and encourages consistency in between mixed and original data, which is crucial besides enforcing confident predictions. We compare LaserMix with other mixing techniques. We observe that mix-up has no improvement over the baseline since there is no distribution pattern in random points. Cut-mix has a considerable improvement over the baseline as the same semantic class points tends to cluster and reduce the entropy in any continuous area. Our spatial prior is much stronger, where not only the area structure but also the area's spatial position has been considered. Meanwhile, we also show the ablation results for the hyperparameters in our framework. Furthermore, we study the best possible mixing strategy in LaserMix. We observe that mixing along the inclination direction is more effective than along the azimuth direction. Our code and benchmark are publicly available. Thank you for listening.